Welcome to the massive open online course on Aspen Plus. In today's lecture, we are going to discuss about fluidized bed. Now, as a chemical engineer, you are already aware of what a fluidized bed is and how it works. But just to recapitulate, I will explain a bit. A fluidized bed is a bed of solid particles which float over a stream of gas. Usually, the fluidized bed looks like this. There will be a vessel in which there will be a perforated plate, and there will be a bed of solid particles that will reside over this perforated plate. So this is the solid bed, and obviously if there is solid particles, there will be a lot of void space between them. Gas will be fed from the bottom, and this gas will pass through this perforated plate and it will flow through this void space and it will move out like this. Initially, the bed will be dense. That means the gas will just flow through the void space and the solid particles will be static in the bed. But as you increase the velocity or the flow rate of the gas, the upper portion of the bed will start expanding. In other words, the upper portion of the bed will start floating on the gas. As you increase the flow rate of the gas, more and more portion of the bed will expand and it will float on the gas. Then ultimately there will be a point when the entire bed will start floating. In other words, there will be no portion of the bed which will be static anymore. And that's called the minimum fluidization velocity. It is written by UMF. If the bed expands like this and all the particles starts floating on the stream, then the entire surface area of a particle will be exposed to the gas. And that is called the fluidized condition of the bed. And why it is called fluidized condition? Because at that point, the entire bed behaves like fluid. Although the components of the bed is solid particles, but the bed as in entirety behaves like fluid. And it will have identical properties as a fluid has. For instance, if you tilt the bed like this, then the bed will adjust itself in such a manner that the top layer of the bed becomes horizontal. Further, if there are two fluidized beds operating side by side and they are interconnected to each other through a channel, something like this. So this is one fluidized bed and this is another fluidized bed. They are connected through this channel. In that condition, the beds will readjust their heights in such a way that they are same, just like it happens with a liquid. And also, if there is a bed and if the fluid flow is very high, then the fluids may create some kind of bubble inside the bed. That means there will be a bubble where there will be no solid inside, and all the solids will be outside the bubble. And this bubble will burst when they come at the surface of the fluidized bed, just like it happens for liquid. So the fluidized bed will have all the liquid-like property, and that's why it is called fluidization. Now, as I said before, during the fluidization, the entire surface area of all the particles will be exposed to the gas. And that's exactly what is needed for the fluidization operation. Because for any chemical engineering operation which grossly depends upon the surface area of solid particles, this kind of fluidized bed will be very useful. For instance, drying. If you have to dry solid particle, then fluidization is very effective. You can pass hot gas, fluidize the bed on it, it will dry very fast. Or if you have to absorb some material onto the surface of the particles, then also this fluidization will be very effective. Or if there is some reaction that you need that to occur onto the particle surface, then also the fluidization will be very effective. So any kind of surface operation or surface-based operation, fluidization or fluidized bed will be very, very effective. Now let us go to the Aspen Plus window and study it further. A fluidized bed module is available over here in the model palette, where the solids modules are available. So you have to bring it over here. So let us do it. Here you see there are two mandatory inputs and two mandatory outputs for a fluidized bed. The mandatory input is solids and gas, and mandatory outputs are also solids and gas. There are certain auxiliary inputs and outputs which you may give or you may not give based on your requirements. First, let us connect them and study it further. Let us name it as S in. This will be solid out. Let us name S out. This will be gas in. So write G in. And this one is G out. Now let us see the blocks B1. This is block B1, our fluidized bed. So you go to the input and see what are the inputs required for fluidized bed. Specification. First you have to specify the bed mass. So what is the amount of bed mass? That is, if this is perforated plate and this is the bed mass. Now, although it is a continuous system, but at steady state condition, there will be a fixed bed mass which has to be maintained. That means if the operation stops, then what will be the net amount of solid that will stay onto the perforated plate? So that is the bed mass we are talking about. You have to specify that bed mass over here. Or you have to specify the bed pressure drop. That means how much of pressure that is being dropped from this point to this point. Actually, bed mass has to be given to calculate the pressure drop only. But if you know the value of the pressure drop, you can directly give it. Otherwise, you can give the bed mass and the pressure drop will be calculated from the amount of bed mass only, because the particle size, density, voidage space already known by the Aspen Plus. So pressure drop will be calculated. Here you have to provide the voidage at minimum fluidization. So that you have to specify. And the Geldert classification. Okay. Here you will find there are 4 types of Geldert classification. Geldert A, Geldert B. There is some Geldert C also for sticky particle when there will be some stickiness in the particles. So for that, Geldert C is there, and Geldert D. Now, what are those functions? Let us study. These are the Geldert specification of particles. You will find this is group A or Geldert A, Geldert B, Geldert C, and Geldert D. Now, what are the conditions? Group A or Geldert A is given for aerated powders, that is, airable particles or materials having small mean particle size or a low particle density, less than 1.4 grams per cc. And these solids fluidize very easily with smooth fluidization at low gas velocities. So it is very fine particles. When you have very fine particles and with a very low particle density, then you can use Geldert A function. Geldert B is for sand-like powder. As you understand, sand will be not so fine and it will be not so light also. So sand-like particles, most particles diameter 40 to 500 micron with a density range 1.4 to 4 grams per cc. So if you have that kind of particles, you will use Geldert B. Geldert C is cohesive or very fine particles. Normal fluidization is extremely difficult for them because of interparticle forces that are greater than those resulting from action of gas. So gas will not be able to separate those particles. There will be some cohesiveness within the particles. They will be sticky. And finally, Geldert D, that is sproutable particles or large and or dense particles. So that is for Geldert D. And all those A, B, C, D, they are given, and you can see how the rho S minus rho F, that is the density of particle, solid particle minus density of the fluid, that is, or density of the gas rather, rho F is the density of the gas. So that difference is a function of mean particle size. So this is given over here. You can refer to this figure. So based on the kind of particles that you are using, you have to choose this Geldert classification. Then comes the minimum fluidization velocity. This is the minimum fluidization velocity. As I have already explained, this is the velocity at which the first time the entire bed is fluidized, or there will be no portion of the bed which is still static. So that is the minimum fluidization velocity. Now, if you have the information of minimum fluidization velocity, you have to directly specify, or that minimum fluidization velocity can be calculated from some correlation. What are those correlations? There are 2 correlations. One is by Wen and U, and another is by Ergun. These are the 2 correlations that can be specified. If you want to see what they are, just refer to this help file once again. For that, you have to go to Fluid Mechanical Principles. Here, you will find the information that we are looking for. The equation from when and u, this is there in a journal paper which you can refer if you want to, can be used for approximate calculation of minimum fluidization velocity in a wide range of condition for Reynolds number 0.001 to 4000, means very laminar to very turbulent, the wide range. So this is the minimum fluidization velocity UMF. So UMF multiplied by dP, that is the diameter of particle, by nu f, this is the kinematic viscosity. So that will give you the Reynolds number, and that Reynolds number is a function of AR, and this AR is given by this ratio rho s minus rho f by rho f. So from there you can calculate UMF, that is the minimum fluidization velocity, by when and u equation. And if you are interested to find out what when and u equation is, you have to simply click this and you can go to this CY when WHU AICH journal volume 12 in 1966, page number 610 to 612. So this is the paper that we were looking for. Okay, and this is the equation that we have just seen in the Aspen help file. So if you are interested, you can just refer to this AICHE paper and study it further. Similarly, you will have another equation called air gun equation. Now, air gun equation is rather common for you because you might have used this air gun equation or Kozeny-Kármán equation for finding the pressure drop in packed bed. So that equation also can be used over here. And then next thing is transport disengagement height. In short, it is called TDH. There are various TDH model over there, and these models are George and Grace, Chen and Knowlton, Fornell et al., and Fung and Hamdullahpur. So these are the four models there. But first we have to understand what is transport disengagement model. Let us go back to the help file once again. Here the theory about the transport disengagement height has been explained. Basically, the fluidized bed model is divided into different zones. Primarily, the dense bed and the freeboard height. Dense bed means where the particles are still static. That is dense bed. And freeboard means where the particles are floating. Now, at the upper surface of the dense bed, there will be a splash zone where the bubbles will burst. The bubbles means outside the bubbles there will be solid particles, they will engulf the bubble. So at that point, the bubbles will burst and there will be some kind of fuzzy transition over here. And this fuzzy transition will end at some point over here where the concentration of solid particles in the gas will be constant. So this entire region above that, the concentration of particles in the gas phase will be constant. So this is the zone where the particles are dense, and this is the zone where the particles are free and their concentration in the gas phase is also constant. Between them, there will be a transition phase, and that phase is called the transport disengagement phase, and the height of that is called the TDH, or transport disengagement height. There are several correlations as I have showed over here. George and Grace, Chen and Knowlton, Fernald et al., Fung and Hamdullahpur. There you'll find that TDH, or transport disengagement height, is a function of U, dB or G, where U is the superficial gas velocity at the top of the fluidized bed, dB is the diameter of the bubble at the surface of the bottom zone, and G is the standard acceleration due to gravity, 9.81 meter per second. So this is how the TDH is calculated based on them. And there is another factor, and that factor is maximum dCV/dH. Now what is dCV? dCV is the concentration of solid particles inside the gas phase. And as the height changes, the concentration of particles inside the gas phase also will change. So there will be a gradient of dCV/dH, and it will have some maximum value somewhere, and we have to specify this maximum value of dCV/dH. Okay, so there is a default value 1 into 10 to the power minus 5. So this default value you can use if you do not have any information, or if you have any information you can type in those values. And finally, elutriation. Obviously, elutriation, already you know, elutriation is that amount of bed mass which will be carried away along with the gas exit. Obviously, there will be fine particles because the heavier particles will remain inside the bed. Only the fine particles will flow away along with the gas. So that is the elutriated material that will exit from the bed. And you will find various equations: Tasirin and Geldert equation, Colakian and Levenspiel, Zenz and Well, etc. There are 6 equations, and all of them are there in the references. So if you want to find out what they are, you can go to the help file. Now, for instance, if you use the Tasirin and Geldert model, you have to provide the decay constant and all those parameters. Here you will find parameters A, B, C. These parameters are there, but what is A1, A2, B1, B2, C1, C2? We have to specify A, B and C, so you may get confused. Other things are given. The elutriation coefficient is this one, gas density is rho g, particle terminal velocity is UTI, and U is the fluidizing velocity. So these are the things that will be automatically taken by Aspen Plus. So they will be given over there. But what about this A1, A2, B1, B2 and C1, C2? We have only A, B and C, right? For that, let us go to the Aspen help file. So the elutriation in fluidized bed has been nicely portrayed over here. At the surface of the fluidized bed, the bubbles will burst, and all the finer particles, they will fly off along with the gas exit, right? So these are the transport of fines. Here you can see the elutriated mass flow of the particle that belongs to terminal velocity class I can be calculated as, this is the equation. This is the elutriated mass flow of particles. ATHB is the cross-section ATHB of bubbling bed at the actual bed height. So the cross-section of bed is a function of bed height. So here there is an option that you can assume the bed doesn't have a constant cross-section. Bed may be tapered. So AT as a function of HB has to be given. If AT is constant, then you can give constant value also. And delta Q is the total inventory. And what is K infinity I? K infinity I is given by this equation. Now all the 6 correlations that you have seen a couple of minutes back, that is Tasirin and Geldart, Kolakian and Levenspiel, etc. How they have been used and how to select them. Some criteria has been mentioned over here. For instance, if your fluidizing velocity is between 0.1 to 0.8 meters per second and the diameter of bed is 0.07, or if it is a rectangular bed, then it is 0.08 by 0.08, and the particle size is between 0.03 to 0.2 millimeter, then you have to use this Tasirin-Geldart equation. And for Reynolds number less than 3000, you have to use A1, B1, C1. And for Reynolds number above 3000, it should be A2, B2, C2. So this A, B, and C. You remember a couple of minutes back we are talking about A1, A2, B1, B2, C1, C2, and we had only 3 factors A, B, C. So what is that A1 and A2? If Reynolds number is less than 3000, then you have to use A1, and if it is more than 3000, you have to use A2. So while choosing the correlation, you provide all the values A1, A2, B1, B2, C1, C2. Aspen will calculate the correct Reynolds number and accordingly it will choose A1 or A2 depending upon where the Reynolds number falls in. And the Reynolds number is calculated with this. Similarly, you have other correlations as well and their criteria has been said. Accordingly, you can find out the K infinity I for each of these cases, which will ultimately be used in calculating the amount of elutriated mass. Next thing is operation. Now here you have the option to specify the duty or the temperature of the bed, because suppose you are drying something, then you have to provide some heat into the system. Otherwise, how the drying operation can happen? So that amount of heat has to be given over here, that information. Next comes the geometry. So in geometry, you have to specify the height of the vessel and the solid discharge section. Now, solid discharge section means at which point of the height the solid will be discharged. You have an inlet of the solid, right? And the exit point is not mentioned. So whether you take out from here or here, or here or here, that you have to specify with a fraction between 0 and 1. So you have to say 1 if it is taken out from the top. You have to say 0 if the solids are taken out from the bottom. And based on where its location is, you have to give the fraction. For instance, if it is taken out from the middle of the column, then you have to write 0.5 over here. So that's how the solids discharge location has to be mentioned. Then the cross section. There are 2 options. One is circular, another is rectangular. If you choose a circular vessel, then you have to provide the diameter of the vessel, or if you feel that the diameter is height dependent, then you have to provide a table over here it will be populated over here. So the location, say 0, the diameter is 1. At location 0.2, the diameter may be 2. At 0.7, it is 5. And at 0.9, it may be 6. At 1, it may be 7. So that means the diameter of the vessel increases with height. That means the vessel is somewhat tapered. So at location 0, it is 1. And at location 1, it is 7. And depending upon 0.2, 0.7, 0.9, wherever it is, the diameter increases from 2, 5 to 6, like that. That's what it means, the height dependent diameter. And if it is rectangular cross section, if you choose this way, then you have to provide the width and depth. That means, so this is width and this is depth of the column that you have to specify. Next comes the gas distributor. Now the gas distributor, it can be through a perforated plate or it can be through bubble caps. Now both of them you are already aware because you have studied these things when you studied distillation column. So in the distillation column also you may have perforated tray or sieve trays, or there might be bubble caps. The theory is the same. The operational principle is same over here. If you choose perforated plate, then you have to specify the number of orifice and the orifice diameter along with the orifice discharge coefficient. This information is used for calculating the pressure drop. Now, if you already know the distributor pressure drop, you can specify it directly over here. Then you do not need to give this orifice discharge coefficient information. Similarly, if you use a bubble cap type of gas distributor, in that case, you have to again provide the number of bubble caps, the number of cap orifices, because bubble cap will also have orifice. The cap orifice diameter also you have to provide. And again, the cap orifice discharge coefficient or the distributor pressure drop information, either of them you have to mention. And finally, the reaction. Suppose you want to use this fluidized bed as a fluidized bed reactor, where some reaction is happening in the fluidized bed, then you have to provide the reaction criteria over here. The similar way that you have learned while you studied the reactor, how you have specified the reaction, whether it is a free radical reaction or kinetic reaction, or you have given the stoichiometric proportion or equilibrium coefficients. The similar way, you have to specify the reaction criteria over here. So this is how you provide the information and perform the simulation. Now let us take an example and learn it further.